I saw the email. I sent an email to you, I think, last Wednesday in regards to that Proctor exam email you sent out, and I asked you if I
Yeah.
could do it this Thursday and next Thursday for
Yeah,
my
I thought
final
I
face.
replied to that. I'm sorry. I remember you asking and sending an email. I really thought I replied. This is Colin, Daniel, right?
Yeah, and it's all good if not. I might have missed it.
Yeah, you
Just to make
certainly
sure.
can do that. I saw that you couldn't make it Wednesday, you couldn't make it Saturday because they wouldn't allow you to take the test then. But yeah, any of those days you wanted to is fine. Uh, was that the only question that you had?
Yeah, well, that and I've never done it in person. What room build? I know we mean J building. What room
I
do I
got
meet
you.
him in?
So I'm in the J building, and basically I'll be on the JC hall. So when you walk in the J building, it's shaped like a V, like this, and it's
Hmm.
got a round part at the end. That round part's the planetarium, and the doors right there are on the back side in the same place right there. But when you come in, if you take the elevator or the stairs upstairs, I'll be the hallway that's closest to the big parking lot. That's the C hall. So the way it
Uh,
goes is A hall's to your right when you immediately come in, the door closest to the big parking lot, and then B hall's the second hall on the bottom. When you go upstairs, it becomes C and D, and C is the one closest to the parking lot. But I'll be somewhere on that. More than likely, I'll be JC 21 or JC 26, but there's a possibility I might be in JC 28 or JC 13 or any of those kind of rooms. But you can find me in there. I might be using multiple rooms depending on how many people show up at any time.
okay. And final question: the formula sheets will be provided during the test, or do I need to bring those?
If you have one printed out, you can bring it. That'd be a great help. I will have them in the event that you don't have them.
Okay. Thank you.
Okay, no problem. I appreciate you asking about that.
Um,
Yes.
this weekend, or I'm just trying to remember what was the last point we could everything was due, like the test and the final.
So the way I made the final is I think you have to have everything done by noon on Friday. So you
This
could,
like
in
next
principle,
Friday?
not this coming Friday, but the Friday after.
Okay,
That's the final exam has to be done by noon on Friday. So that gives you as early as I think Friday of this week up till Friday of next week at noon for your final, and that also gives you as early as Saturday of this, like 2 days ago, up until Monday of next week that you can do the last face-to-face test.
and it was what of next week?
Monday of next week is when you can take the actual face-to-face, the test three face-to-face. That's the last day you
Okay,
can take that. I think I might have set the date in it to Tuesday in case we had any incidents, but you should be able to knock that out by Monday. If anything bad happens, I can still push it back to Tuesday.
okay,
But the big thing is everything's got to be done by noon on Friday.
got it.
Good questions. Anybody else have any other questions like that?
Yeah, I have a quick question real quick. This is John.
Yes, go for it.
So for the face-to-face three, like the chapter 10 through 11, 14th, I don't see it uploaded yet. Will it, because I plan on taking it at the testing center on Friday. Will it be uploaded then?
Yes, yeah. In fact, I've been toying with different ways I'm going to implement it. So it could be. I was waiting for anybody to let me know that they had someone to take it, and I'll make sure I have it there by then. But it might be a paper test. It might be an online test. I'm not sure yet. That's why I haven't made up my mind or haven't submitted it yet. But
Okay,
I
no
did
worries. Thank
submit
you.
the request, so the testing center is ready to seat you. It's just a matter of when I get the test there.
Okay, cool. Thanks.
No problem. I saw some more people come in. I think I got everybody. That's good. Anybody else have any questions? Trying to get my
Just
iPad
going over
ready.
the last question you said, like for the final, did you decide on if that was a still multiple choice or if that was going to be not multiple choice?
I still have not made that decision. I'm trying to get out of the multiple choice area just because I've had so many people cheating. It's really bothering me. So I've caught like probably 8 cheaters in the last year. I don't
Jesus.
like that. Yeah. And for that reason, I'm trying to get out of the multiple choice, but where you have to show me all your work. So that's what I'm leaning to. But if I can't get it done in time and have it be a reasonable test that's not really hard, then I'll have to go back to the actual multiple choice. But that's
All
why
right.
I sent that warning where you got the email and I said, hey guys, if y'all are banking on memorization, you might want to relook at that. I had a student come in take one of my online tests, and they were done in like 3 minutes, which is memorization, and they did really well. But the problem is, if that's pure memorization where you actually didn't learn how to solve the problems, then you've just shot yourself in the foot. And not only that, if you're on any kind of assistance, no one's ever going to pay for you to retake that class, but yet you've missed every opportunity to learn it. So that's my big fear. If that student
Okay.
happened to have worked all of them so much that they were just in his head, that's great. I mean, that's awesome, and I would never want to take any points off for someone that because that's exactly what doing a lot of problems works. But in one of the cases that I had like that, I literally caught the student in real time looking up something online.
All right.
Anyways, sorry about that. Try to get all that. But here's the good news. Since it's actually already 5:30, I should go ahead and tell you guys this. So I've been warning everybody that I have some way where I can help you improve your homework score at the end of the semester. Uh, and it's important that you not let anybody else know. I don't necessarily do this usually. I certainly am not going to be beholden to do it every semester, but what I've decided to do is at the end of the semester, I will compute your grade uh, with your homework, and then I'll compute your grade without your homework. Uh, and the higher of those two grades is the grade that you'll get. So if you're one of the students that your homework grade is bringing up your total course grade, then I'm going to use that homework. But if you're one of those students whose homework grade is bringing their overall course grade down, I'm going to throw that homework right out. So it will not harm you at all. It just, also will not have the opportunity to help you. So that's what it is, and that's sort of what I had planned from the very beginning of the semester to do. It's just I can't tell my students that because I've done that in the past and told students, and they ended up literally like if I had a class of 24 students, somewhere between 1 and 4 students would actually solve homework problems, and literally every other student would fail every test because they didn't do any homework. So that's why I haven't done that. That's why I haven't announced that. But that is going to be done. And additionally, do not take this as an opportunity to not take your third face-to-face test. But I am going to drop your lowest face-to-face test. So you have 3 face-to-face tests, and I'll take only your 2 highest. So that's 2 ways that your grade is going to get a lot better. Anybody have any questions on that? All right, and there's one more announcement I want to make. I did make, as you've all seen, I made a practice test for the final exam. I made a practice test for the last face-to-face test, and that practice test for the last there you go, Eden. Uh, the practice test that I made for the last face-to-face test includes chapter 14, and the practice test that I made for the final exam includes 14 and 15. To actually go through those banks and cut out the parts that I'm not planning on testing you on that last face-to-face test and on that final, that would take me many, many hours, and it's just something I couldn't afford the time to do. So what I did was, and this is probably better for you anyways, because I would rather you have a more thorough understanding of the chapter to do all your homework and even preparing for the test. But when the test actually comes, I'm going to test you on a much smaller set of chapter 14 and chapter 15 questions. So what I'm in the current process of doing is I'm making you a separate uh, what I'd call a separate practice test. It might even be a separate practice test for chapter 14 and a separate practice test for chapter 15. You're not going to be graded on them. It's you're still getting your grade from the practice or the practice online tests and for the practice final exam, that's still going to go into that pool that has the potential to bring your grade up by 5 points on your final exam. But in addition to that, I'm giving you guys a sort of written practice test that'll give you the answers as well, and it's more indicative of what I expect of you from chapter 14 and 15. I'll post that probably tonight, and I'd highly, highly, highly advise you to look it over. And the vast majority of the questions, it might have like 20 questions, but literally like 15 of them will be conceptual questions that you should be able to just look at and answer. It means it doesn't take any work. It literally either requires you to just look at the problem and then make the answer, or maybe makes you look at the problem, take two numbers and divide them, or take two numbers and add them, or take two numbers and multiply them, and that's it. So that's a more realistic representation of the parts of chapters 14 and 15 that I'm going to test you on. 14 in the online, the last face-to-face test, but 14 and 15 on the final exam. So I just wanted to let you guys know that I am doing that. Hopefully you find that helpful, and please, please take the time to look it over. Okay. That being said, I would say your last face-to-face test that you took would, if you can do all of those problems, that's a good indicator that you understand the material well enough to do the final. Uh, some of the big processes that I expect from you from chapters 1, chapter 2, chapter 3, 4, on up through 11, and then 14 and 15. Almost all of those, other than obviously 11, 14, and 15, were covered in that last face-to-face test. And therefore, if you can do that, you're probably in a pretty good spot. So keep that in mind as well. Anybody have any questions now that I introduced all that new stuff?
So I actually do have a question.
Yes.
So you said earlier that the tests are kind of like cumulative.
Mhm.
So should we be like you said to me that like it was the questions that we most missed on exam one and exam two, and it'll kind of build up.
Right.
So should we be expecting like those similar questions, even if it is like written down, like
Yeah.
handwritten?
Yeah, even if I end up making it a non-multiple choice question, it'll still be those same questions. And let me explain to you, when you see a question on that face-to-face test, te face-to-face test two or something, I could take that question and just change the numbers in it, and I still consider that the same question. So that's the way I could actually implement that. That's the important part of what I was meaning when I sent that email and said, "Hey guys, if you're relying on memory, make sure you know how to do it, because if you just remember memorize the answer and you try to do that problem and I change the numbers, one, if it's multiple choice, you're not going to have any kind of prompt to see which one's the right answer. You have to remember it cold. And two, if I change the numbers, your memory is not going to work at all because the numbers are entirely different. So the answer will be entirely different. Does
Okay.
that make sense?
Yeah, that makes sense.
Okay. But as I said, the practice tests are always the very best way to prep. It's just in this case, I've got that issue with chapters 14 and 15, so that's the only negative side that makes that moderately less good.
Okay. All right. And then I sent you a message privately. I think I texted you like very like late at night one night.
Gotcha.
And you can completely respond to me like after class.
Okay.
I understand. But yeah, just letting you know.
Gotcha. No problem. I remembered seeing your name, and actually, I got yours, and I think I got two other students that texted me over the weekend. I was just too swamped to get to it, and I figured I'd
I
answer
understand.
them today. But yeah, I'll get to them. And if you don't see me get to them, just send me another one, and I'll respond immediately. This weekend was a little hectic, so I didn't get to respond, and I had to put it off till today. But then today, a bunch of fires happened. I had to take care of those, so we'll move on from there. But yeah, make sure if y'all have any questions, you let me know. Uh, soon as your lab instructor gives me your lab grades, I will put that in my grade book so that you'll have not only a accurate reflection of your course grade, but you'll have a updated one that includes your lab grade as well. So when I input those grades, I'll let you guys know, and then you'll know, oh, this is my total grade, not just my lecture portion of the grade.
Okay. I actually, sorry, I don't want to take up the whole time, but
No, you're good.
I was, I know me and a couple other students were having issues with Professor Johnson. He said that he would update like some grades, and like we've been like waiting on them. So like for example, like I submitted an assignment, but I submitted it as a zip file because it was the Excel sheet and the document, and he
Right.
wanted me to resubmit it, so he gave me a zero. So I saw the zero,
And now
and
it
like I
hasn't
don't know
done
if
it
you could
yet.
kind of give him a kick in the foot or you know.
Yeah,
Um, but I just don't like right now my lab grade is like a 60, and I know it probably would be like a
it's going to
90
be a
or an
lot
80 right
better.
now.
Yeah.
Yeah.
Yeah, don't stress out too much about that. I know all of us teachers, including Dr. Johnson as well, they sometimes have those issues. But yeah, I'll try to make sure that's done. The big thing is make sure that he actually makes the changes. I can't imagine he wouldn't. He's a good guy. I know he's not going to try not to. He might forget, which would be a problem. But if that comes up and he forgot and never did that, then definitely immediately tell him, hey, I don't think you did this on such and such a test, and he'll address it. If he doesn't address it, then you have to come to either me or you go to our chair. But once you go to the teacher, that your responsibilities are done with that teacher to do it, and then from there on out, you go to the next chain of command. Not that I'm in any way, quote unquote, over him because I'm the lecture teacher, but sometimes the lecture teacher can get a little bit more work and get the person to work with them a little more quickly than going through the process of asking the chair, or then the next step is our dean, and then the next step is our president of college, and you don't want to do all that.
Yeah, of course. Me and a couple other students have emailed him. We just haven't gotten a reply back. It's been like a week or two about now because he ended
Yeah,
lab like maybe like before break ended or the Thanksgiving break.
gotcha.
So we've just been
Yeah,
waiting, and
I'm
I
sorry
understand
about
with the
that.
holiday.
Yeah, I'm sorry about that. I don't want to say anything bad because I've been in that spot too. Hopefully he'll reply to you really soon, and I'm real sorry about it happening either way. And I got to apologize for how many times have I had a text message that someone sent me or an email that someone sent me that I didn't reply. So, but yeah, let me know if you have any problems with that not getting done. I will talk to Dr. Johnson about it. But once you talk to him, if you don't get what you need, just come back and you can ask me, and then I'll talk to him. And if that still doesn't work, and I'll help you go to our department head, and that'll get it taken care of.
Okay, thank you, sir.
No problem. All right. So, as I warned you, chapter 15 is going to be another shortened version of chapter 15. So, we're not going to cover all the material. I highly recommend you read all the material because there's a lot of good stuff in there that can help you no matter what your major is. So, it's definitely stuff that's worthwhile. But what I want you to do is make sure that you know how to do very specific problems. So, in chapter 14, we learned about simple harmonic motion. Specifically, that was motion that started off with a very specific differential equation that was m d2x over dt squared equals negative kx. Anything that obeys that differential equation is called simple harmonic motion, and it can be written, like I said, m d2x over dt squared equals negative kx. That can also be written as, notice I'm going to use the dot formation here, so it can also be written as m times x double dot plus, notice I pulled the minus kx on the other side, so it's plus k times x is equal to 0. That's another form of the simple harmonic oscillator equation. And another one still is if you divide through by m, then you get x double dot plus k over m x is equal to 0. And that one's probably the most useful way because when you have no coefficient in front of the x double dot, then the coefficient in front of the x is the square of the omega quantity. And you know that the solution to that equation is x equals a cosine kx, or excuse me, omega t plus phi. So that was sort of the big part that you have to understand from chapter 14, so that when you look at a differential equation, you can know immediately what goes in front of the t inside the cosine. You know what goes in front of the cosine as well, because that tells you what the amplitude is. And you know from the initial conditions what the phase constant is. So you can add that phi, for instance, within the cosine. Well, there's something like that in chapter 15 as well, but the differential equation is different. So I want to start off by showing you that. So let's go ahead and share the screen with you. So this should pop up any second now. Okay. So what I was saying earlier was chapter 14 gave us something like this. We had m x double dot plus kx equals 0, which could also be written as x double dot plus k over m x is equal to 0. And that meant that x is equal to a cosine omega t plus phi, where omega is equal to the square root of k over m. So notice how this quantity is related to this quantity. So once you have the spring constant, or, we showed you, for instance, in chapter 14 that this was for a mass on a spring, but we also showed you that, in fact, there was several other versions of motion that gave simple harmonic motion as well. For instance, a mass on a pendulum. As long as the angle was small, we got the same equation. In that case, the omega became the square root of L over G or something like that. Same thing for a torsion pendulum, same thing for a physical pendulum, and it became something each time. But the main thing is whatever is in front of the x when you have a coefficient of just 1 in front of the second derivative of x, when this number is 1, whatever's here, the square root of that is what goes into this slot right here. So that's a key thing that you have to understand about simple harmonic motion. Now, and I just showed you that, by the way, just to show the parallels between chapter 14 and chapter 15. So here's chapter 15. Whoa, that was neat how it did that. Chapter 15, we're going to have a different equation, and this equation is called the wave equation. Okay, this equation is what we call a PDE, a partial differential equation, and it looks like this. There's a second order derivative of some quantity that does the wiggling. The quantity that does the wiggling in this case is going to be capital D of x and t. And this is the second derivative with respect to x is equal to, I'm going to leave a space here because something goes in there, but I just want to leave the space first so you can see the beauty of how one side looks like the other. The other side is going to be the second derivative of d of x and t with
Sir, are
respect to
those
time.
D's or is that a Greek letter?
That is the partial derivative symbol. So notice how it looks sort of like a backwards cursive D that they let part of it off of. It also looks like the Asics logo for the shoes Asics. That,
Yeah,
yeah, this is what hopefully you learned in your lab to some extent, but you might not have since you had
generally it was always just shown as a D. That's why I was
gotcha.
asking.
So what it really means is that function d of x and t, that's a function of many variables. And the left-hand side is what you do if you pretend that t in that function d of x and t, if you pretend that t is a constant and you just do a regular derivative, that's what the partial of d with respect to t with respect to x is. And then
All
if you
right.
do it twice, you get the left-hand side. If you do the same thing on the other side, this time you'd let the x be a constant, but the t be a variable. Then you take the derivative. That's the partial derivative with respect to time, and take it a second time, and that would be the right hand side. Does that make sense? So
Sure.
that's
I'll,
yeah.
I'll have to go over it a couple times.
Yeah, it's a little weird, but it's not that hard. Let me give you an idea, for instance. The derivative of x times y with respect to x. Now, I could have made that x times y look a little less horrible, but here's x times y. So if I take the derivative of this with respect to x, then I'm pretending like y is a constant. So literally, I could say if I had 4x and I wanted to take the derivative of that with respect to x, I'd get 4. Well, what I did there was I pretended y was 4. So the answer is clearly 4, which is y. So the derivative of that with respect to x is just y. Similarly, if I had the derivative of x times y with respect to y, I would pretend the x is a 4, for instance, and I'd say 4y, and the derivative of 4y with respect to y would just be 4, but 4 was x, so the answer is x in that case. If you want to see another version, you could say the derivative of x squared y z with respect to x would be 2x y z. Because remember, this is like 2 times 3 times 4 or something. Because the y is a constant and the z is a constant as well. If you wanted to take the derivative of that with respect to y, you'd get x squared z. And if you wanted to take the derivative of that with respect to z, you'd get x squared y. So does that help you better understand what I mean by partial derivatives? And feel free. I mean, it still should take you a little time, but it
Uh,
should be a little easier to wrap your head around now.
yeah, I'll be honest, not really. I've done normal derivatives in
Mhm.
calculus before. I don't think I've ever actually seen partial derivatives.
Yeah, it normally doesn't come up till sometimes you get into it in the second semester of calculus, but usually you don't get to it until the third semester of calculus. Uh,
Oh, yeah, I've only taken Calc 1.
yeah. So just keep that in mind. That's something that like I've warned you guys, when you're in engineering or the physical sciences, a lot of time you're going to learn your math from your physics teacher, your engineering teacher, as opposed to a math teacher. And that's going to be the case always. You're never going to have enough math when you come into a physics or engineering class. They're always going to have to teach you more. So that's part of the problem. Anyways, so that's what a partial derivative is. Now I got to finish what I was talking about as far as the wave equation. So I'm almost finished with the
All
wave
right.
equation. The part that I'm missing on the wave equation is this. You have right here there will be some constant between the derivative and the equal sign, and sometimes it'll be right here next to the derivative with respect to time. But they could also write it where it's over here, in which case you got to figure out, hey, I've got to get that velocity down here in the bottom and next to the time. Because that velocity is something I can ask you about. Like, I can give you a differential equation like this wave equation and say, what is the velocity of this wave? Let me show you an example of this. Example. So if I gave you, for instance, this example wave equation, as I wrote right there, the second derivative of d with respect to time equals 4 times the second derivative of d with respect to distance, or x, and I say, what is the actual velocity? You should be able to transform this in such a way that you can figure out what the velocity is. Does anyone know right now what the velocity will be? Just quickly off the top of your head. If you don't, it's perfectly fine. I got to finish out the example, but it's a good thing to try to, type in on a chat or whatever if you think you know it. Now, what I have to do is I realize the only way the wave equation works from a unit standpoint is if velocity times time in the bottom is happening, because if velocity is multiplied by time, you get x, which is the same thing that's over here. So the only way that this can really be equal, or this can be equal to this, is if this velocity is squared and it's multiplied by this time squared, and on this side I have distance squared. Okay? So that's how I keep my mind about me and my wits about me to try to make sure I understand exactly where the velocity has to be. So what I see right now is I could make this equation into the second, well, let me go ahead and write it. The second derivative of d with respect to time squared is equal to 1 over 1/4 times the second derivative of d with respect to x squared. But then I'd say, well, wait a second. If that 1/4 is the actual velocity squared, then velocity squared times x squared gives me meters squared per second. And that's not what's on the other side. On the other side, I just have seconds squared. So that can't work. So I know that's not right. What I should have done is multiplied both sides by 1 over 4. So in reality, what I should do is say 1 over 4 times 1 over 4. And now I'm going to get uh, second derivative of d with respect to x squared, okay, is equal to 1 over 4 second derivative of d with respect to time squared, like that. And therefore, the square root of 4 has got to equal the velocity, and therefore the velocity is 2 meters per second. Everybody follow how I did that? So that's one of the things you have to be able to do, is recognize the format, not only of the simple harmonic oscillator equation so that you can figure out what omega would be, but also of the wave equation so that you can figure out what the velocity will be. Not only that, by knowing the wave equation up front, you know what's doing the wiggling uh, when Maxwell and Faraday and all these people were working on Maxwell's equations. They knew that light was a wave because you can do simple experiments like you can pinch your fingers really close together and then try to look through the hole between your fingers. And what you'll see is a repeat of your fingerprint right in between your fingerprint for your index finger and your fingerprint for your thumb. You'll see a little line that is a reflection, if you will, or a repeat of your thumbprint, and then you'll see another line above it that's a repeat of your index fingerprint. And you might even, if you look close enough, you might see yet a second copy of your index fingerprint and a second copy of your thumb in fingerprint, like that. So I can see that, and what I know is happening there is something called diffraction and interference. So that shows me definitively that light is a wave. But the problem in the 1800s was they knew white light was a wave, but they couldn't figure out what was doing the wobbling. In this case, you immediately see, oh, the D, whatever the poop that is, that's what's doing the wobbling. So now that we have the wave equation, there exists yet another wave equation too. And that one's called the baby wave equation. So let's go ahead and kill this as far as an example. So we have the wave equation. Okay, there it goes again. We have the wave equation. And the wave equation says the second derivative of d with respect to x squared is equal to 1 over v squared times the second derivative of d with respect to time squared. And this automatically offers a solution that is d of x and t is equal to some a. Now, the book used cosine when we did simple harmonic motion, but when we're doing wave motion, it actually chooses to use sine. So I'm going to do that as well. And what we get is a couple different ways you can write it. You can say it's the sine of, and your book takes the time to write it like this. I'll put a square bracket there. I'll put a 2 pi over the wavelength, and then I'll put a parenthesis x minus v times t. Now, if you take the derivative of this with respect to x, and then you take the derivative of that result with respect to x, you can put that in the left-hand side of the wave equation. And then if you take the derivative of this with respect to t, and then take the derivative of that result with respect to t, then you'll get the derivative on the right-hand side of the equation. And if you put them in there, you'll see that they actually satisfy the differential equation. That's a fair game type of question for your final exam as well. Okay. But in addition to that, what you need to know is that this is a wave traveling in the positive x direction. So that's a wave traveling in the positive x direction. And now I can also say there's another solution, d of x and t. Uh, Maybe I'll put a prime on it because it's going to be technically a different one. In this case, it's a sine 2 pi over lambda times x plus vt. This one is a wave traveling in the negative x direction. So I'm going to write this with green. I'm going to say wave traveling in negative x direction. Okay. Notice the difference. The difference between the positive direction being a minus and the negative direction having a plus there. Now, I know when I was told that, I did not like the fact that someone suggested that I sort of memorize it. And that really is the lowest rung of learning. So just memorize it to get started. But now let me show you how I can confidently say that I know what I wrote there was the positive direction when I used the minus and the negative direction when I used the plus. What you have to realize is these wave equations look something like this. So if I had a graph like this and it's a graph in time, it would look something like this, right? If it's a graph in space, it would look like this as well, okay? The distance from here to here and the time axis is the period, and the distance from here to here on the space axis is the wavelength. Okay, now that's peak to peak, but it's also trough to trough, and it's also this point to a similar height point, skip one. So all of those are wavelengths. Now, if you wanted to refer to a certain point, let's say this point right there, you know this wave is moving this way to the right or moving this way to the left, something like that. But if you wanted to find that particular point, all you'd have to do is set the argument of this trig function to a constant. In the case of that dot, the constant, since it's sine x, would be x equals 0. So if we set the 2 pi over lambda times x minus vt, if I set that equal to a constant, let's say 0, then I'd be finding out where that point moves in time. And actually, it'd be more helpful to do it in this graph, because in the x graph, this thing's going to be moving by, whereas in the time graph, it's sitting perfectly still. So let me explain what I mean by that. So uh, to understand motion of a single part of the wave, we set the argument of the trig function to a constant. I'm going to make that constant just a big K, just for the heck of it here. Student just came in. Let me let them in. So what does that mean? Well, what that means in the case of D equals A sine 2 pi over lambda x minus vt, like that, then what I'm going to do is say 2 pi over lambda times x minus vt is equal to some constant k. Now, since that's equal to a constant, let's solve for x and see how x behaves as t increases. So first thing I'm going to do is multiply through by k over, or by lambda over 2 pi, and I'm going to get x minus vt is equal to lambda k over 2 pi. So that's another constant, but it's still a constant, and that's a key point, okay? Now I'm going to solve it for x, and I get x is equal to lambda k over 2 pi plus v times t, which shows you as t increases, x also increases. And remember, what we're talking about as x is that one spot on the wave. And what we just found is as time goes on, x increases. So it's literally moving in the positive x direction. Everybody get that argument I just made there? That's key to understanding this wave motion. Anybody have any questions on that? Because I'm getting ready to do the one moving in the negative direction, so you'll see that it's also moving in the negative direction. So if D was equal to A sine 2 pi over lambda times x plus vt, then I would set that equal to a constant. I'm going to say 2 pi over lambda, 2 pi over lambda times x plus vt is equal to some constant k. That's going to give me x plus vt is equal to lambda k over 2 pi, and that's going to give me x is equal to lambda k over 2 pi minus vt, and we see as t increases, x decreases. So that's showing you that as time goes forward, this wave, that one spot on the wave, will be moving to the left now. So it's actually going in the negative x direction. So are y'all now understanding that x plus vt is a negative traveling wave and x minus vt is a positive traveling wave? Anybody have any questions on that? Okay. So another way we can do this is we know, for instance, there's some equations that come in handy when we're dealing with wave motion. So I'm going to make use of that a little bit. And for instance, one of the things we know is omega is equal to 2 pi times the frequency, which also gives you the frequency is equal to omega over 2 pi, or it can give you that yes, it can give you yeah, I think that's good enough. Or you can also see that frequency is equal to 1 over the period, which we learned about the frequency in chapter 14 as well. Remember, frequency would be measured in, for instance, hertz, which means cycles per second. And period would be measured in seconds, for instance. And this is called the angular frequency, and that would be measured in radians per second. Okay? So, with all that in mind, it's common for us to write D is equal to A sine kx minus omega t instead of all that junk I wrote. And the reason why is because we have defined k as 2 pi over the wavelength. And if you took that original version, let's write that out now. That original version was D is equal to A sine 2 pi over lambda times x minus vt. If I multiplied through by that, I would get A sine kx minus kvt. Everybody follows me so far, right? Anybody see any problems with that? Now, another expression before I move to the next step, another expression we need is velocity equals frequency times wavelength. And this one's the other wave equation. We call this the baby wave equation because it's just multiplication and division, whereas the real wave equation is a partial second order differential equation. So that's kind of a big deal. So that's why we call this one that. Now, when you see that, then watch what happens now. It looks like all of you, nobody asked me any questions on how I got the kx minus kvt. So I'm going on assuming that y'all understood that. And what I have now is, oh, I didn't mean to write equals there, is I have the sine of kx minus, now here's the part, k was 2 pi over lambda, and v is equal to frequency times lambda, and then t. So what you see happen here is the lambda on the top cancels out with the lambda on the bottom, and the 2 pi f, notice, is that frequency right there. It's that angular frequency. So what we get is A sine kx minus omega t. And that was what I said we were going to switch to, is kx minus omega t. And this is a wave moving in the positive direction. Okay. Similarly, D equals A sine kx plus omega t is a wave traveling in the negative x direction. Okay, everybody follow that? Now, not only that, but you can now figure out what the velocity is, because check this out. if you set kx minus omega t equal to a constant again, let's say that big K, then what you see is x can be found to be K plus omega t divided by lowercase k. So what you see is x is equal to k over lowercase k, which doesn't really mean anything. That's not anything that helpful. But what does matter is you get plus omega over k times t. And what that tells you is the x has some fixed constant value, which we've chosen to write as k over little k. Oops, I didn't mean to erase that. I meant to erase the other part, but here we are anyways. So, so what we see is the x is moving with a velocity given by this quantity right here. That is called the phase velocity, and that's the velocity that we're dealing with. V equals v phase. There's another one called the group velocity, but I'm not testing you on that. I'll tell you what it is just so you'll know and you'll see it from reading. But in this case, the phase velocity is just omega over k. And you can see that pretty straightforwardly by realizing omega is 2 pi f and k is 2 pi over lambda. You can see now that the two pi's cancel each other out, and you end up getting, in fact, f over 1 over lambda, which is the same thing as f times lambda, which is exactly the baby wave equation I already told you about. So now you can see that when I give you a wave function, a times the sine of kx minus omega t, I can take the omega and divide it by the k, and that will give me the actual velocity. By the way, I mentioned to you V group. Again, don't worry about what that means right now. You'll learn later. That's d omega over dk. Uh, that's just something that you should know for future endeavors. But what we're dealing with here is we're going to deal with the phase velocity, and that's just how fast a particular spot on a single wave is traveling either to the left or to the right. Anybody have any questions on that?
Yes. Why in God's green earth did they choose in the same formula to have to capital and lowercase k? They look exactly the same.
Okay, this is where I take the blame on that because I'm the idiot that used K.
Okay, sorry. I
No,
thought
that's
maybe
okay.
that
It's
was like
it's
the official one and I was losing my mind
I
trying to
know, and
keep
it's the
track of
second
that.
time I did it today, so I really feel bad for myself, for my students for putting up with me. I was like, well, I did it and it didn't cause any problems, so I'll go with it again. Yeah, that wasn't a good idea. You can call it anything you want, though, okay? You can just call it
Okay.
C if you wanted to. Uh, all right, with all that in mind, now I want you to have some understanding of what we do when we're talking about a wave. I want to reiterate, of course, the parts of a wave. So let me quickly draw a coordinate system, and I'll actually draw two coordinate systems to make a point here. So this is d, that function we were just talking about, and this is x, one of the arguments of the sine function. And in principle, the way we've got it written is that, let's see here, let's see here. Let's see. I'm going to go halfway down here, and then I'm going to go here. So this is the way a wave is supposed to look. Something like this. And this one should come up right about there. Okay. Again, as I told you, from peak to peak, that distance is the wavelength. Also, from trough to trough, that distance is a wavelength. Also, from any random spot to that same height random spot, skip one, that is also wavelength. Okay. But notice that's in a D versus X graph. I'll also say that this quantity is the amplitude, and this quantity is also the amplitude. Everybody follow that? Now I'm going to make another graph. This time the axis, the horizontal axis is going to be time, and the vertical axis is going to be D. And again, I will draw going up, going down, going up, down, going back up. Okay. Now, in this case, this time from peak to peak is the period. And this time from trough to trough is the period. And this distance in time from a random height to skip one to the next random height is also the period. We also know that frequency is 1 over the period. And we also know that omega is 2 pi times the frequency. And finally, if you were to stand on a pier, let's say at 17th Street, and the instant a wave is, the crest of a wave is directly under you, you start your timer. If you stop that timer when the next wave crest is directly under you, then and you get 0.5 seconds. Do you know what that time is? Is that the frequency? Is that the velocity? Is that the period? Hopefully that's somewhat obvious. Anybody? Okay, so you're standing on a pier. A wave is coming in from the ocean towards the shore. A crest of a wave is directly under you, so you start your timer. And then that crest drifts on, and the trough is under you, and then the trough drifts on, and then the next crest is under you, and you stop your timer. Anybody?
Period.
Yes, very good. That's the
So
period.
I believe Ryan actually answered it first in the comments.
Yeah, he did. I saw that just as it's popping up. That's good. I figured it was more or less someone was thinking and not paying attention to this. But the main thing is, yeah, that's the period. Okay. Now that also told us something. Remember, velocity equals distance divided by time. And we know the distance from a crest to a crest. What's that distance called? The distance from one crest to the next crest.
Period.
Exactly. Without the period in this case, this is a distance as opposed to a time.
Is it wavelength?
Exactly. Wavelength. Good job. And I knew what you were thinking. I think it was Daniel. So that's the wavelength. And then how much time was that went by? What's the symbol we use for that amount of time? It's the period, right? So we know the velocity, this phase velocity that we're talking about, the velocity is the wavelength divided by time. But that means the same thing as the wavelength times the reciprocal of time. And according to this expression right here, that means it's the wavelength times the frequency. So we get velocity equals wavelength over period, or it equals wavelength times frequency. And that is our baby wave equation. So now, hopefully, you have an understanding of why the baby wave equation is V equals F times lambda, or V equals lambda over T. Anybody have any questions on that? Okay. Now that we've got all this out of the way, go ahead.
Actually, I do. Why is
Yes.
it only baby wave. Does it change when the waves get bigger
Oh
at
no,
a certain point?
I said that earlier, but you probably missed it. It's the baby wave equation because the real wave equation is a second order partial differential equation, that big nasty thing.
Ah, okay.
So that's the wave equation that us calculus people do, and this is the wave equation that algebra people do.
Okay.
So I call it the baby wave equation because it's like baby math. Now, here's the neat thing. There's a very specific type of wave, and it's made up of these things. Let's see if you can guess what they are. I'm going to start off with drawing a line. Now, I'm going to make a mnemonic in real time here. I want y'all to listen to it. It's my homage to Rush Limbaugh. And I think I've said it to you guys before, but it's great, great excess. Notice how I'm spelling excess, X hyphen CESS. Great excess undermines various industries, Marxism rules. Again, this is my homage to Rush Limbaugh because I listened to Rush Limbaugh since '87, watched him on TV, and listened to him on the radio since 1987 up until the day he died. Well, he quit a little bit before that, but for a long period of time. And he repeatedly called teachers, especially college teachers, as pinky commies. So I'm using that own expression. Great excess undermines various industries. Marxism rules to pay homage to him. This is a very specific set of waves called the electromagnetic spectrum. And one of the things you're going to learn from this chapter by reading it is that certain types of wave have a distinct velocity. For instance, the velocity of a wave on a string is equal to the square root of the tension divided by the mass per unit length. The velocity of a wave in a fluid is equal to the square root of the bulk modulus divided by the density. The velocity in a rod is equal to the square root of the elastic modulus divided by the density. So those are all things that have a very specific velocity given by very specific physical characteristics, and that means a mass on a or excuse me a wave on a string. Its velocity is the square root of the tension divided by the mass per unit length. The velocity of a wave through a fluid, like the sound going through water, you might think since the density of water is so much higher than the density of air that the speed of sound in water would be slower. But it turns out that bulk modulus B up there is so much bigger than the bulk modulus for air that it turns out the velocity of sound underwater is quite a bit higher than the velocity of sound in air. And that's why if you're a scuba diver, one of the first things you learn about sound is that it's omnidirectional. Your ears cannot discern the difference in timing well enough to see whether the wave of sound hit your right ear or your left ear first. And that difference in time is what your brain uses to say, hey, that sound came from over there or back there. Because we don't have that ability, because the water makes the wave of sound go so much faster, we can't tell what direction it is. All you know is you hear a sound and it sounds like it's coming from everywhere. But anyways, now that we know that, it turns out that the electromagnetic spectrum has a very specific velocity. That velocity is c, the speed of light, and c is 299,792,458 meters per second. And it's literally that number followed by a decimal point, followed by an infinite number of zeros. Okay? And we know that because when Maxwell put his equations together, he ended up getting an equation that looked like this. And when he did a calculation of that epsilon zero times mu zero, epsilon zero is 8.85 times 10 to the negative 12th. And it's got some units. I'll just leave that off for right now. Mu zero is 4 pi times 10 to the negative 7th. If you multiply those two numbers and then you flip them over and then you take the square root of that, you'll get the speed of light. And that's what Maxwell discovered when he put his equations together. He not only figured out, oh, wow, I know what light is and I know what's wiggling, but he also understood where the speed of light came from. And it tied in these two quantities, this epsilon zero and this mu zero, turn out to be very important in electricity in the case of epsilon zero and in magnetism in the case of mu zero. But there's not really a good reason for them to be related until you see this wave equation come in. And lo and behold, you've got a very good reason, because epsilon zero times mu zero, if you take the square root of that and the reciprocal of it, you get the speed of light. So that was what it was. And that's what gives us this electromagnetic spectrum. So all of these types of radiation, can anybody guess what G is? I'll give you a hint. Incredible Hulk.
Gamma,
Yep. And then
uh,
X,
X-ray,
U,
ultraviolet,
very good. And V,
visible,
I,
infrared,
exactly. M, hot pockets.
microwave,
And R,
radio.
okay. Notice the Roy G. Biv that you probably all learned from grade school has to be backwards in this. And another problem you have to be able to solve is this one. What is the wavelength of waves sent out by slash at AM 850? So that's a typical question that you could expect on the final exam. There's some things that have to happen. Let me explain how that works. AM implies this is a radio wave. And specifically, the AM means amplitude modulated. So if you actually looked at the sine waves that come from an AM station, you'll see they don't have that same consistent amplitude. The amplitude goes up and down and stuff like that because it's amplitude modulated. The actual sound wave is in the wiggle of the amplitude. But in addition to that, that means a couple things. One, it means that it's EM radiation, which implies V is equal to C, which is approximately equal to 3.00 times 10 to the 8th meters per second. That's 300 million meters per second. The other thing that AM means is that 850 implies 850 kilohertz, which means 850 times 10 to the third hertz. Okay. So it seems like when I ask you that question, like you don't get enough information. They only gave me AM something. Like if you didn't even realize that was the frequency, you wouldn't even know where to begin. But now at least you can say, oh, well, AM means that's the frequency in kilohertz, so I can at least figure out the wavelength. But the baby wave equation says you need the velocity and the frequency in order to figure out the wavelength, or you need the velocity and the wavelength to figure out the frequency, and so on and so forth. But because we know it's a radio wave, we know its velocity, so I can go ahead and say the wavelength is equal to 3.00 times 10 to the 8th meters per second divided by 850 times 10 to the third hertz. And that gives you wavelength 850 AM is equal to 351.9, I think. Let's double check that math. Or 24 or something. So 3 10 to the 8th divided by 850, 10 to the third, 352.94. Now, remember, a meter is about 39 and an eighth of an inch, roughly. So this is considerably bigger than 352 yards. So you might, in fact, say it's about almost 5 football fields, is how big that wavelength is. So it might be reasonable for us to conclude that the right hand side is long wavelength, and therefore the left hand side would be short wavelength, and we'd be exactly right. Okay? Now, the fact that velocity is equal to frequency times wavelength, and all these types of radiation, gamma rays, x-rays, ultraviolet, violet, infrared, green, yellow, orange, and red, microwaves and radio waves, all of them travel at the same velocity, so that you see, since v has to be a constant, the baby wave equation says when the wavelength goes up, the frequency goes down. So that also tells us that this is uh, high frequency and this is low frequency. Now, there's an equation from quantum mechanics that says energy is equal to h times frequency, and therefore we see this is the high energy end and this is the low energy end. And it probably makes some sense for us to say this is the high temperature end and this is the low temperature end. So all of that stuff that you should know. Not only that, I can tell you something kind of neat. The violet here is a wavelength of 450 nanometers. The red here is a wavelength of 700 nanometers. And it just so happened that God gave us a little bit of help in our memory work by making the frequency of the violet 7.0 times 10 to the negative 14 hertz and 4.5 times 10 to the negative 14 hertz is the frequency for the red. Isn't that wonderful? You got the same mantissa for both numbers. 450 leads to 7.0 and 700 leads to 7.0, or excuse me, 4.5. So that's kind of neat as well. Now let me show you one more question. What is wavelength FM 93.7? So we've got the same rigmarole here, only there's a different rule for FM band. If you know it, by all means state it. Anybody know what the frequency is in the FM band? In the FM band, the frequency is in megahertz. So that means times 10 to the 6. So I'd write down 93.7 times 10 to the 6 hertz. When I do that math, I go 3 times 10 to the 8th divided by 93.7 times 10 to the 6, and that gives me 3.201 meters is the wavelength. So now you can see evidently the FM band is a shorter wavelength, but you can also see, red is a longer wavelength than orange, and violet is a longer wavelength than ultraviolet, and ultraviolet's a longer wavelength than gamma rays, and so on and so forth. Anybody have any questions on that?
Kinda. I was just wondering, why is it microwave radiation is dangerous, but radio waves and infrared really isn't, if it lies right in the middle of those?
Microwaves aren't necessarily all that dangerous. Like they're passing through us all the time. That's literally the radiation that comes from cable stations, dish network, and all that stuff. So that's literally coming through the air all the time. A microwave oven is dangerous because it sets up a standing wave inside of it, and that wave has just the right frequency where it can make specific molecules, water being a big one. For instance, if you ever tried to like microwave talcum powder, which is completely dry, you'll see that it doesn't get significantly hot. But if you take and mix some water in that and then microwave it, it'll get really hot. So it takes microwaves takes very specific molecules that can resonate with that frequency and makes them flip back and forth. And that's a huge energy change from one state to the next, to the next, to the next. And that agitation is the very definition of high temperature. If you increase the average molecular velocity, the velocity of the molecules, that is the definition of increasing temperature. But other than
Does that
that,
mean you could
microwaves don't hurt you too terribly bad. They're not great for you, but
does that mean you could technically do that with radio waves?
yes, the problem is the radio waves are normally a frequency that doesn't respond that well, or doesn't. The atoms and molecules that we interact with daily and are in our bodies do not resonate at those frequencies. So that's why it doesn't happen with radio waves.
Okay.
Now, the reason why the gamma rays and X rays hurt you is obviously they're a lot higher energy, and that higher energy is the ability to actually cause a problem in your DNA replication. And if you have a DNA replication that goes bad, the vast majority of them there's no big deal, but some of them actually lead to what they call the lucky frog, which means you could have something that benefits your particular instance of a species over the fellow species. Maybe you grow an extra vertebrae in your neck and you're the descendant or the ancestor of giraffes. So one time that happened, you got one extra vertebrae in your neck. A second time that happened, meaning your children or your grandchildren had the same anomaly. They got two extra vertebrae, and then your great 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 grandchildren maybe got two other vertebrae, another vertebrae. Over billions of years, you could actually, or at least millions, hundreds of millions, you could actually end up becoming a giraffe that has this huge long neck because it's advantageous of you compared to the other species. Now, what also happens is, again, the vast majority of these anomalies in the DNA does nothing. It doesn't make the lucky frog, nor does it make this other thing, but it can make a faulty replication, and a faulty replication of DNA, if it repeats itself, if it can basically reproduce with that DNA as it's newly copied, that's the very definition of cancer. Cancer is a DNA that replicated itself incorrectly, but now usually replicates itself quicker than the cell it used to be. So that's why the higher energy ones can actually affect us because they have a better chance of screwing up our DNA. That's one way of looking at it, anyways. Anybody have any questions on that? All right. So there's a couple problems I showed you. Some other problems you might want to be able to know is your book talks about transverse waves versus longitudinal. If I took a rope and I tied it, way over there to something, and then I shook it up and down, what I would see is a pulse would climb down that rope like this. And when it got to the other end, if that other end was fixed tight, then when it got there, that hump, that shape like this, is going to lift up on whatever it's tied to. Newton's third law says that that loop is going to feel a force in the opposite direction. That's going to make the hump that was on the wave like this, that's going to make it become a trough instead, and now the wave's going to come back to us upside down. That's what happens when a wave encounters a end that's not free to move. If it encounters an end that's free to move, then it'll come back right side up. Now, that's a transverse wave, and in some sense, you can't make any sense of that on a longitudinal wave. But to make a longitudinal wave, instead of me taking a rope, I take a really long spring and I tie it to that distant spot on the wall. And now, instead of going up and down, I'm going to go like this. When I push those springs together, the coils, which were like this, come together, and that causes compression. And then when I pull back, that causes expansion, or what we call rarefaction, R A R E F-A-C-T-I-O-N. What you see is the wiggling is going the same direction of the as the velocity, and that's called a longitudinal wave. When the wave wiggles perpendicular to the velocity, that's called a transverse wave. So that's something else that's useful to know. I would say, for instance, example 15.2, we only have about 4 minutes. So here's example 15.2. And like I said, I'm going to put some chapter 15 and chapter 14 questions up there so you'll know better what to do. But with me explaining all this, those should be fairly straightforward. In example 15.2, it says a wave whose wavelength is 0.30 meters is traveling down a 300-meter long wire whose total mass is 15 kilograms. If the wire is under a tension 1,000 newtons, what are the speed and frequency of the wave? So V equals question mark and frequency equals question mark. First off, I know it's a wave on a string, so the velocity of the wave on a string is equal to the square root of the tension divided by the mass per unit length. And the mass per unit length is the mass, m, divided by the length. That would be 15 kilograms divided by 300 meters, which is 0.050 kilograms per meter. Let's double check that math. 15 divided by 300 gives me 0.05. Yeah, that's good. So now I can say the velocity is the square root of 1,000 newtons divided by 0.050 kilograms per meter. That gives me the square root of 20,000 meters squared per second squared. So the velocity is going to be equal to the square root of that, which is 141.4 meters per second. So that's the velocity of the wave. Now we know velocity equals frequency times wavelength, and we have the wavelength, so the frequency has to be equal to the velocity over the wavelength, which is 141.4 meters divided by 0.30 meters. And that gives me 471.4 hertz equals the frequency. So that's a typical problem. There's another one, example 15.3. Let me read this to you. It says an 80-meter long wire, 2.10 millimeters in diameter, made of copper wire, is stretched between two poles. A bird lands at the center of the wire, sending a small wave pulse out in both directions. The pulses reflect at the ends and arrive back at the bird's location 0.750 seconds after it landed. Determine the tension in the wire. So what they're doing there is they're saying, okay, you can determine the velocity by realizing that that pulse went a distance of 40 meters and then another 40 meters back. So that's 80 meters in 0.75 seconds. So if you take the 80 meters and divide it by 0.75, that gives you the velocity. Now you can set that equal to the square root of the tension divided by the mass per unit length. But the mass per unit length you can get because they told you the wire was copper. So you can look up the density, 8.9 times 10 to the third kilograms per cubic meter is the density. And if you take that density and multiply it by the volume, which is power squared times the length, then you can get the mass. So this example 15.3 allows you to calculate the mass per unit length by using the density and allows you to calculate the velocity by doing that 80 meters divided by 0.75, and then from all that you can get the tension. So example 15.3 is another one you should be able to do. I just explained it because we're running out of time, But like I said, you should be able to do that. And we're actually out of time, so you guys are completely free to go. You don't have to meet me for class anymore. Or and I assume that's the case for your lab as well. You don't have to meet Dr. Johnson for any lab meetings as well. The only time you have to come in the future is to take your face-to-face test, which you can do at the testing center or one of my testing times. Or when you go to take your final exam, again, you can do that at testing center or one of my exam times, but that's the only time you have to come. That being said, all those times that I'm available for taking the test, you can use those as office hours. If it gets too loud, I'll just step out in the hall and work with you, or I'll, do something else like I can set up Zoom meetings or anything like that. So all of that's completely open to you. I'll be posting that stuff and I'll send you an email later on tonight or whenever I do post that stuff. Have a good one and thanks for coming and feel free to give me a text or email anytime. Someone said the last face-to-face test is due this Sunday, correct? I actually allow you to take it up till Monday, and I've even set it where it doesn't disappear till Tuesday in case anything happens. But yeah, I would ideally like you to take it sometime this week. Friday at the latest would be best, but you can even take it Saturday or even Monday if you need that extra time. That's for the face-to-face test three. The final exam, however, has to be done by a week from Friday at noon. It has to be finished by noon. That's right, Zachary. Appreciate that. Anybody else have any questions? I'm going to wait for the last person to leave in case anybody has any questions. You can also look on my YouTube channel for me doing these same examples that I didn't get a chance to do now. I took the time to explain it instead, but check that out. And I'll try to put some links in our modules too.
So there's no class on Wednesday?
No class on Wednesday.
All right.
All right. Have a good one.
Um, good.
You can still, if you need me and you want me to meet you online at that time, just give me a holler, send me a text message or something, and I can still, show up for a Zoom meeting at that time, even though you're not required to.
Okay. I did have a question about one of the chapter 14 homework questions.
Okay, no problem. That's okay with me, Zachary, regarding the Monday. That no problem. You want to pull up the question and share it with me, or you want me to pull it
Yes.
up?
I can pull it up. It was problem 14.78. Uh, actually, I'm not the one doing the Zoom. I don't know how to
Okay,
pull it up for it.
14.78. Gotcha.
Yeah, it was the 10th question.
Okay,
It,
I'm
it, it
gonna
was the
open
one
up.
where the guy stands onto the wooden raft and then after he steps off, figure out the oscillation. And
Gotcha.
frankly, it since it really just gives the weight of the raft and how far it sinks and nothing else, it didn't give like time or spring constants or anything. I wasn't able to figure anything out about it.
Gotcha. So let me look at this the standard view, and I'm going to just make sure this is the right question. I'm going to say stop sharing, and now I'm going to share a new screen, specifically this one. This is the problem you're talking about?
Yeah.
Okay, so it says a 330 kilogram wooden raft floats on a lake. When an 80 kilogram man stands on the raft, it sinks 3.2 centimeters deeper into the water. When he steps off, the raft oscillates a little while. So, what they're expecting you to do is imagine that the water is acting just like a spring, so that when the
Yeah,
additional
but I
80.
couldn't figure out what the spring constant was.
Okay, so the spring constant is going to be you take the 80 kilograms, multiply that by 9.8, and then divide it by 0.032 because that's the x in meters. So I'll say 80 times 9.8.
Oh, I was using the entirety, like I combined 330 and 80 together for like
Yeah,
the
it's just the
for
additional amount that's
point.
added.
So like 80 is I used the entire one for mass, but afterwards, but I use for the spring cause I just used the 80.
Yep. So I got 2.45 times 10 to the fourth for the spring constant.
All right. Back
Now,
in, okay, spring constant, that was mass divide. No.
that was the force, the 80 kilograms times 9.8
Yeah. Okay,
divided
force
by the point
divide
zero
by,
three two.
okay, by distance, right? So, okay.
Now, the other part is when you go to calculate omega, that's the square root of k over m. In this case, the m has to be the 330 kilograms.
Okay.
So now you can say that the frequency, which is omega over 2 pi, you're going to take the k, which is the 2.45 times 10 to the third, and divide that by 330. That gives me 74.24. Now I'm going to take the square root of that, and that means omega is 8.616.
Wait,
In
wait,
order,
wait. You went really fast there
okay,
for the second one.
gotcha.
Okay,
So,
so E was what?
so omega is the square root of k over m. We figured out k was 2.45 times 10 to the fourth.
Right.
If you divide that by 340, that's omega squared. So if you take the 2.45 times 10 to the fourth divided by 330 and take the square root of that, you'll get 8.616. That's
Okay.
omega. And now you have to divide omega by 2 pi to get F. So when
All
I
right.
take that 8.616 and divide it by 2 pi, I get 1.37. So I'm going to call this 1.4 because it asked for two sig figs. So I submit that, and it says that's right.
Wait, hold on. 245 times 10 to the fourth divide by 330. Oh, right, square root.
And then take square root, right?
8.6.
1/6. Now that's omega, and they're asking for F.
Yeah,
F is
and
omega
then
over 2 pi. So you got to divide that uh,
uh
8.616 by 2 pi.
okay. 8.616 by 2 pi. 2 pi. Okay, 1.37 hertz.
Mm-hmm.
All right, and then use that to get the energy?
Yeah, the energy, you're going to use the formula 1 half kx squared.
Right. All right.
And
I'm
that one
sorry.
wants two sig
I
figs as well.
swear I spent like all weekend trying to do physics, just none of it stuck to my head. I
Yeah.
swear to God,
Well,
I
that's
don't know
weird.
how I got an 80% on the second test. I don't know how I did it. I don't know. I should have failed that one. I don't know how I didn't.
It was a miracle. Don't worry about it. Somebody was helping you,
Okay. It
giving you
was
the confidence you needed.
okay, 1/2 K
X squared.
KX squared.
It's actually K amplitude squared, but since the person stepped in it, that made the maximum amplitude the X that they caused. So I'm using the X, but in reality, the total energy is 1 half K A squared, not X squared.
Okay. Oh, okay. I was starting to get confused why we were talking about that one. It's like, oh wait, no. The question we were working on was that the energy is a separate one from frequency. I didn't see you scroll.
Right.
Like,
Gotcha.
oh, okay.
Does that make sense now, Colin?
Yes.
Yeah.
Yes. Thank you. I will do my best. That's all I can swear because like
No
it's
problem. I'm sure you'll do fine, Colin.
yeah,
Sawyer, did you
yeah.
have a question, sir?
Um, yeah, I just wanted to know because my grade is an 89.45 right now, does
Right.
that round up
Right.
to an A or is that still a B plus?
It's still a B plus, but once your lab grade gets in there, I if your grade really is 89.4, I can't imagine it's going to go lower. I'd imagine if anything, it's going to go higher. So that would be more than enough. Even if your grade is only like a 92 in lab, you're probably going to be enough to push it up to an A. And not
Okay,
only that, remember you got 5 bonus points on your final exam if you got 100 on all those practice tests.
thank you. Have a
No
good
problem.
evening.
Thank you, Sawyer. You have a good one. All right, that looks like it then. So everybody have a good day. Enjoyed seeing you. I'll be posting chapter 14 and chapter 15 problems later. Bye bye.